Okay, in this video I want to talk about how to do Gaussian elimination. And again, this is just like when we have a complicated system of equations and we turn it into a triangular system of equations so that it's easier to solve. We're going to take a complicated matrix and turn it into an easier row echelon form, which is essentially going to be triangular, that is then hopefully going to be easier for us to solve. So our general strategy is to first get a 1 in the top left corner and then use that 1 to eliminate anything below it. So even if there was some other easier way to do elimination, typically in Gaussian elimination we're going to make a 1 in the top left corner and use that 1 to get rid of stuff below it. You'll see why once we get into the method. Once we're done with that, we're going to leave the first row and column alone and then repeat the same process with the next leading entry. So we're going to make leading ones one at a time. Okay, so the way we're going to actually do it, so it's going to look like normal elimination, but I've written my steps in this way. So one thing that we're allowed to do is swap rows. So we mentioned before that a matrix is not in row echelon form if it has rows of zeros on top, but we're allowed to swap rows. So if I did see rows of zeros on top, I could just swap them so that the row of zeros was on the bottom instead. I'm also allowed to multiply a row by a non-zero constant. Keep in mind that a row represents the coefficients on a linear equation. And so if I take an equation and multiply it by 2, then it's going to be an equivalent equation. So I'm allowed to multiply an equation by a number, so I'm also allowed to multiply a row of this matrix, which represents an equation, by a number. And the last thing I'm allowed to do is I'm allowed to add one row to another row, or I can combine that with the previous step, and instead of adding just one row to another, I can add a multiple of one row to a second row. Okay, anyway, let's just try it with an example. So I have a nice simple system of equations with two variables here. So I'm first going to write the matrix, which is 2, 6, 2, 3, -1, 13. And this is an augmented matrix, so I'm going to use my vertical line. My first step is to make the top left entry into a 1. Okay, so I could maybe try and subtract rows from each other, so maybe 3 minus 2 to get a 1. But I think since the top row is already, everything is even, I'm just going to multiply the top equation by 1/2. So I'm going to do 1/2 times row 1. So 1/2 is a constant. I can multiply an equation by a constant. That will give me 1, 3, and 1. 3 minus 1, 13. So the one downside of using matrices is that we do end up repeating. We keep writing the matrix over and over again, and so sometimes like this row doesn't change for a good while, but I have to keep copying it because I don't want to lose track of how many rows there were originally in the matrix or which row is where. So we do have to rewrite the matrix. That's the only downside of this method. Okay, so I've successfully made a 1 in the top left corner. I've made a leading 1. Now I want to use the leading 1 to get rid of stuff below it. So in order to cancel out a 3, I need to make this into a -3. And so since you're multiplying 1 by a number, it's usually really simple to figure out what to multiply by to cancel whatever number you need to cancel. We just multiply by the negative of whatever that is. So I'm next going to do row 2 minus 3 times row 1. Okay. Here's the place that it's going to look a little strange. Is up until now, when I had to add an equation to a multiple of another equation, I just went off to the side and actually wrote out what they were. And I'm trying to save myself some writing here. That's the whole point of matrices. So I'm going to see if I can come up with a way to do it without all the extra writing. So you could try and do it in your head, like 3 minus 3 times 1, -1 minus 3 times 3, and so on. I feel like I'm going to screw that up. Like my memory is not that great. So what I'm going to do is I'm going to take row 1 and multiply it by -3. And I'm going to write those numbers somewhere in here. I'm actually going to pick right here. So 1 times -3, 3 times -3, 1 times -3. And I'm writing them in as though they were exponents just because I need to stick them somewhere, but I'm actually putting them right next to the numbers that I'm about to add or subtract them from. So normally I would be taking 3 minus 1, 13, which is my row 2, and I'd be taking minus 3 times row 1, which is minus 3, minus 9, and minus 3. And then I'd be adding them. But I'm trying to save myself some writing. I don't want to have to write this. So I just stuck these numbers in as though they were exponents, or in the same location as if they were exponents. They're not exponents. I'm adding. This is what I'm doing. I'm just putting them in just so I have somewhere to stick them. Okay, so my top row I'm not actually going to change. I'm going to leave it as 1, 3, 1. Even though for our middle step we did multiply it by 3. And then my bottom row, we're going to do 3 minus 3, which is 0. Negative 1 minus 9, which is negative 10, and 13 minus 3, which is positive 10. Which is the same thing we would get if we actually did it off to the side as taking a row and taking a multiple of another row and then adding the 2 to get our new row 2. We'd still get the same answer. I'm just trying not to have to write this every time I do a step, because for a more complicated matrix, like a system of equations with 3 equations, 3 variables, we're going to have to do a lot of elimination. I don't want to have to write this down every single time. So instead I'm writing down these little numbers as these are the numbers I'm going to add or subtract. Okay, so let's look at what we managed to accomplish. We got a 1 in the top left corner. We used that 1 to eliminate the entry below it. There was only 1 entry below it. So success, this first column is exactly how I want it to be. Leading 1 and 0 is below it. Next thing I want to do is look at the second row and say, I want this to be a 1. And so I'm going to have to do another operation to make the first non-zero entry of the second row into a 1. But again, just like this step was pretty simple, I think I see how to turn a negative 10 into a 1, which is just divide the row by negative 10. So divided by negative 10 or multiplied by 1/10, we would end up leaving the top row alone and multiplying by negative 1/10, you get a 1 and a minus 1. Okay, so if you stare at this matrix, this is a matrix that's now in row echelon form. In order to actually solve from this point, I'm just going to turn it back into a system of equations. This corresponds to a system of equations. X plus 3y is 1, y is minus 1. And so the nice thing about going through this extra steps to make sure that our coefficients are 1 is that this bottom equation is going to be really simple every single time. It just explicitly says variable is equal to particular number. And when I plug it into the equations above it, so using my substitution method, x plus 3 times negative 1 is equal to 1. That's a negative 3, so I just have to add 3 to both sides to get x is equal to 4. So the nice thing about doing this, making a leading 1, is that your algebra steps in the back substitution are very, very simple. We never have to worry about dividing by a coefficient. It's already been done. We already made a 1, so we just have to move the numbers to the other side and we're done. So the solution of this system of equations would be x is 4, y is minus 1, or the point 4, negative 1.